looking faults, it needs some type of directional supervision so that it can operate for only forward faults, or if set, only reverse faults. This is a distance relay, different than an impedance relay. In most relays, most terminology today, people intermix the two terms, distance and impedance. So this measures the distance on the line. It is a self-polarized characteristic because its characteristic passes through the origin. And it has a set reach, and this is the referred to as a mode distance characteristic. This is a characteristic which is cross-polarized or positive sequence polarized. And we'll discuss an example of this later, but this characteristic is an expanded characteristic and includes the source impedance that's back at this point in ZG. And this point and the set reach are on the diameter of the circle or circumference of the circle, but they represent the diameter of the circle as well. So it's an expanded characteristic. This characteristic is referred to as an offset mode distance characteristic, where you have a set forward reach and also a set reverse reach that looks in this direction. And it also needs to be directionally supervised to avoid tripping for faults that may be in this region back here. Reactance units, again, reactance units measure just based on the reactance, and you would have a setting which would either be an impedance or a reactance reach and a resistance reach associated with that. And we'll talk more about this characteristic. It also needs to be supervised, because in computing the reactance line, you also compute the negative line. Quadrilateral characteristic, this is just a basic form. There are many forms of quadrilateral characteristic. You can define the upper and lower boundary and the resistance boundary left and right. And again, this characteristic also needs to be directionally supervised to have a forward region and a reverse region. This is an example of relays that existed back in the 1990s and is a relatively good concept, but it's a switch zone quadrilateral characteristic where you'll have a zone 1, you'll have an overall operating characteristic and a zone 1 level reactance, and then after some time delay, zone 2 level, and then zone 3 level. And they're all controlled by the same resistance reach. And similarly, a mode distance characteristic where you have reactance lines that separated into different zones. A lenticular characteristic, which is a combination is a variation of the mode characteristic. This was ideal for very, very long lines where you did not want the full mode characteristic. Let's talk a little bit about phase comparators now. You have phase comparators and you have magnitude comparators, and phase comparators were first invented with the electromechanical relay back in the 1950s time frame, but it basically compares the phase angle relationship of two phasor quantities. Namely, in this case, I have S1 and S2. And in this case, where S1 leads S2, you have an operating region. If S1 were to lag S2, you would have a restraining region. In the electromechanical days, well, they still exist today, as a matter of fact. You have this S1 quantity is VAB, the voltage from here to here, or the voltage from X to Y, okay, that is input into this particular winding. And then the voltage from Z, okay, again to Y, but it's across this at 90-degree phase shift to this. It's across this pole right here. And basically what happens if S1 leads this quantity, all right, you produce a rotating field that operates in the operating direction. If S2 were to lead S1, then the field would be rotating in this direction, and you would have a restraining operation. And just to come up with an equation that you have your applied quantity, this voltage right here, Vxy, all right, is the result of this loop equation around here. So that would be VAB from here to here. The voltage drop across the compensator, which is IA minus IB ZR, would equal to this quantity right here. Similarly, you have the voltage drop around this loop here, which is this quantity. And as I said before, where Vxy leads VZy, you have a XZY sequence and you trip. Otherwise, you would restrain. The distance relay characteristic, basically, if you have this is a self-polarized characteristic, to give you an example. And if you draw two segments, straight line segments that intersect this at point on this circle, and then back to the length of the diameter from one point to the other, this angle is always 90 degrees no matter what point you are on that circle. And that gives rise to this type of characteristic, because now I can separate this quantity into a fault quantity, which is IZ, which is the fault current times the impedance to the fault at that point. And that's the fault voltage. And then you have a set quantity, which is IZC, which is the current that's flowing through the compensator, or the impedance setting, if you will. So I can produce this quantity right here, all right, which is the IZC minus IZ that you see here. And then the polarizing quantity is this value right here. Now I've rotated it by 90 degrees, okay, to give it in this direction. This value here is rotated. So here I'm looking at the angle relationship when I'm at this point of the circle. They're 180 degrees, or basically 0 degrees apart. It's neither lagging or leading. All right, but when the fault is within the circle, you can see that the JIZ quantity, this quantity, is lagging the polarizing quantity, and therefore you have no operation. You have an operation. All right. When the fault is external to the circle, you can see that this quantity here is leading this quantity, and therefore you have no operation. Be patient. There it is. Okay. To have a cross-polarized or positive sequence polarized, I use the cross-polarized as an example, is that you're including the source impedance. So you can only measure quantities at the relay. And of course, the fault voltage at the relay, you only see this portion of the voltage. But if you look at the healthy phase, for example, a phase A to ground fault, you look at phase BC, the voltage should reflect what the source voltage is, except for any voltage drop due to load. Okay, so in this manner, you can include the source impedance into the fault calculation, and such that where this quantity right here is the fault voltage. All right, and so we use the BC quantity, for example, as the polarizing quantity, and the S2 quantity, which is the fault current time to compensator minus the voltage. So that will produce a larger circular characteristic. Now, I have just taken this quantity right here, rotated it, okay, by the minus 90 degrees to give me something that is normally in phase with this quantity, such as I previously showed. When it's outside the characteristic, it is lagging this quantity, and therefore you would, it's leaving this quantity, therefore you would have a trip. And where it's inside the circle here, that I might have said that backwards, you would be doing just the opposite. And the next two slides just show some typical values that are used for V-operate and V-polarize, and the advantages and disadvantages of each. And like I say, V-pol, I refer to cross-polarized. That's using the VAB of the healthy phase, but you can also use positive sequence, which is a very common polarizing quantity. So those are the charts on those two slides. All right. At this minute, I'm gonna ask Ryan, would you send me a text message? I don't know if I'm getting my questions forwarded to me. I don't see where they would be showing up here. Well, I'll continue. Here I referred previously to a magnitude comparator, and that's basically looking at a quantity SA and SB, whether SA leads is outside the circle or greater in value magnitude than SB or not. At this and this is just an example. It shows the relationship between a phase comparator and a magnitude comparator. And you can go back and look at the phase comparator to see how the phase angle between these two quantities compare. Or you can substitute in these equations and come up with these magnitude comparators to see how it operates. Because in some cases, some people use magnitude comparators to compute the characteristics. apologize. I just wanted to check to see if I lost a screen in the background here, and I did not. Okay. Perfect. Development of other distance characteristics. Here I show you a lenticular characteristic, and that is done in the same fashion that a mode characteristic is done, except now we, instead of giving a full 180 degree region of operation, we're only given this region of operation that's plus or minus 45 degrees. And changing that to 135 degrees, you get what's referred to as a tomato characteristic. And then these are equations related to quadrilateral character, or let's say the reactance line characteristic. You can readily see that if I just take the imaginary part of the fault impedance, I can compare it with the sec x of c. Okay. At the same time, I can compute this quantity x of c minus z and see where the angle is greater than 90 or less than 90. All right. And where that angle between these two. And with quadrilaterals, all you can do is determine whether the fault is across this forward line or not. You can't discern faults in the reverse direction, and therefore you have this reverse line that looks in the reverse direction. So you end up with a plus x of c line and a minus x of c line. And again, that has to be directionally supervised. Similarly, you have the resistance, and again, you can measure the load resistance or the fault resistance in the load direction or in the minus load direction with these sayings, but you're restricted here between this line and this line. Again, so directional supervision, and when you put those together in a quadrilateral characteristic, you will see that they need to be directionally supervised. Another reference that gets into more mathematics of the computation that's done on modern relays is addressed in this reference. Let's talk about apparent impedance fault loops. There are 6 fault loops measured by each zone. And the fault types you have is phase to ground, phase to phase, 2-phase to ground, and 3-phase. And as you see here, we have the A to ground fault, A to ground loop, the B to ground loop, and the C to ground loop. On the lower part, I show the phase-to-phase loops. The phase-to-phase loop, this is the AB loop, this is the BC loop, and this is the CA loop. All right, I do not show a loop. Those are the faulted loops, and I do not show a loop for 3-phase faults, but I will illustrate it in this example. Whenever you have a 3-phase fault, what you want to do is look at the apparent impedance. And this is my source impedance. This is where the relay is applied. I have a voltage measured at the relay, all right, and then I have a current that's measured at the relay, and I'm going through some fault impedance here. Because it's a 3-phase fault, all 3 phases sum to 0. All right, therefore, in the return path, there is a drop. And so, therefore, simply my voltage drop or apparent impedance is ZL1 here. all right, which is just VA over IA. For a phase-to-phase fault, I look at IAB. My fault loop is this direction right here. Okay. I have this impedance in twice right here. This is where I'm measuring. So VAB, okay. And I have IA in this direction and a minus IB. All right, but we know that IA is equal to minus IB. So, but anyway, looking at this equation, that's what my impedance is equal to 2 IA ZL1. So my apparent impedance is still ZL1, the same as it is for a three-phase fault. And it's the ratio of VA minus VB divided by IA minus IB. And as I say in the note at the bottom, the phase mix is set in terms of positive sequence impedance. This is apparent, again, this is the phase to ground loop. If I look at my phase to ground loop, I'm going A, this is where my relay is. I'm measuring this impedance and with this fault current. And then down here I have 3I0 returning in my ground path and this return ground path impedance. So it's VA, all right, is equal to IA times this value plus 3I0 times this value. So that's this quantity right here. So given that, my apparent impedance, okay, is equal to this quantity here, okay, which is basically VA over IA. All right. And the angle, I just want to point out, is the angle of my positive sequence impedance plus this impedance here. All right. So my angle will be modified. All right, as well as the size of the circular characteristic. My ZG is my ZL1 plus ZLN. Well, we normally do not set the relay in terms of Z0. We set it in terms of Z1 and a KN factor or a K0 factor. And so on this particular slide, I go through some gyrations, if you will, but I substitute the value of ZLN here of ZLO minus ZL1 divided by 3, which is the value of that ground return impedance. All right, and with that, I come down here and determine that my ZG is equal to my positive sequence value times 1 plus KN, where KN is equal to this term right here. All right, and then my ground angle, of course, would be the positive sequence angle plus or minus whatever this angle turns out to be of this quantity. Okay. All right, I have a question. I finally found them, and I apologize. It says, on the motor circle, could you go into more detail regarding the leading and lagging and how to distinguish that? Okay, on the motor circle. So I will have to go back up a few slides. All right, I'm not sure of exactly the circle. At this point, right here, I have taken this quantity Iz and have multiplied it, okay, by minus J. So I've taken this value right here, rotated it 90 degrees in this direction, and that's what this quantity is. So at this point here, I'm looking at two phasors. I'm looking at a phasor, okay, that is defined by ZC, the compensator, minus Z. Of course, they're both multiplied times I. Okay, so I'm looking at that voltage phasor that's in this direction as defined at the edge of the circle. And I'm also looking at the fault quantity, fault voltage, that after being operated on by minus J is in this direction. And as you can see at this point, they are 180 degrees apart. So if the fault is inside the circle, you can see that IZC minus Z, this quantity right here, is leading this quantity. Okay? If it's to the counterclockwise direction, less than 180 degrees, it's leading. And at this point right here, which is outside the circle, you can see that this quantity here, ZC minus IZ, you can see that this quantity is lagging this quantity. So therefore, by leading or lagging, you will have determined the operation. I certainly hope that addresses the question. Okay, MTA stands for maximum torque angle. That's the angle at which you get maximum operation. Let me escape here. I believe this is about where we were when I went back. I've got MTAG. When you set the mode characteristic, the positive sequence characteristic, for example, you set a line angle at, a line impedance value at a line angle. That line angle is often referred to as not just the line angle, but the maximum torque angle. For energy-based relays, like an electromechanical, that's the angle at which maximum torque is produced, either closing or opening if the fault is along this line. All right, and so that is a term that has grown in the industry that represents either the line angle, or it could be the maximum torque operation for a directional unit, but that's where the maximum closing torque or maximum opening torque or restraining torque is produced at a particular angle. All right. We had talked about that Kn factor, and I just want to point out that there are two factors used by different relays in different manufacturers. There is a Kn factor that is for compensating the residual, or 3I0. It is all the residual, or 3I0. It is all the same basic equation. But it's a matter of terminology, whether you're going to have 3I0 in this equation or I0 in this equation. because if you have 3I0, this value is divided by 3. If you have I0, you have what this value is. Okay, so just be wary when you're setting relays as to the definition of what this Kn factor is, because it is not always the same. And also the ground reach is set in terms of the positive sequence impedance and the Kn or K0 factor up here. Faulted phase selection. The importance of faulted phase selection is to correctly identify the faulted impedance loop. This is particularly important for single pole tripping, event recording, fault location, what have you. For fault location, for example, you've got to know which fault location or which fault loop is being operated to apply the correct algorithms to get fault location. And if you look at, except for phase to ground faults, all your non-ground faults, you have common phases that are involved. In other words, a CA fault, or let's say a CA fault can also impact the C to ground unit. A B to ground fault may impact the BC unit. So forth and so on, but you can see the commonality between here, and nothing is cleanly isolated. And on this page, there are a list of several factors. I will let you read them. But basically, these are issues that are resolved with directional supervision and or some type of sequence current or voltage supervision, that you can easily manage these conditions. All right. Okay. Then you have a two-phase to ground fault. It's really the culprit. The phase to ground unit of the leading phase will overreach your reach setting for forward external phase to ground faults, and the phase to ground unit of the lagging phase will underreach. All right, and these issues are the result of the phase to ground fault and must be resolved with accurate phase selection. And just to give you an illustration, this is the characteristic of a two-phase to ground fault, a BCG fault, and the leading phase, BC, is phase B. And I have these lines, the green line, the red line, and the blue line, going up in this direction, which are a function of the source impedance ratio. And for the underreaching element, I have the green line, red line, and blue line. Okay, again, a function of the source impedance ratio. So I refer to this as a two-phase to ground bullet. You have the overreaching characteristic and the underreaching characteristic. And so, and as you move in this direction, the fault resistance is increasing. So therefore, with high source impedance ratio and the larger the fault resistance, it is likely, unless you do things correctly, that you may have a misoperation of a phase to ground unit, okay, for a two-phase to ground fault that's beyond the length of the line. Note also what I have plotted here is the operation of the BC unit. It's right on the money. it operates correctly. Okay, so again, this is how the comparators operate. Okay, that where phase selection is not taken into account yet. And this is a good paper that discusses that. So you can refer to it to get more information in regard to different techniques to detect faulted phases. The location of CTs and VTs. The reach of a distance relay is measured from the location of the voltage transformer. Directional sensing occurs from the location of the current transformer. In most applications, VTs and CTs are usually the same location. That is, there's no measurable impedance between them. But their location should always be considered, especially for applications with transmission lines terminated with transformers. Here we're going to talk a little bit about step distance protection, and where I have three zones: zone 1, zone 2, and zone 3. Okay, somebody asked a question. Let me pause a little bit. I have jet lag or some kind of lag here between looking at these messages, but somebody asked the question as to what comparators ABB relays use: cross-polarized, memory polarized, or positive sequence polarized. Well, we use a combination, actually all of them. In some cases we have positive sequence. I believe the new generation includes positive sequence and memory, such that the factors are weighted, that you have 15% memory and 85% of the positive sequence quantity is used, such that if you were to measure zero voltage, you would at least have what the 15% of what existed before the fault. I hope that answered the question. Where we use cross-polarized, you basically use a memory voltage that dies with a that gradually reduces with a let's say a filter effect, that your 60 hertz, you have a 60 hertz decay that's associated with the memory voltage. Okay, but here we're talking about the step distance protection, and we have these three zones defined in both directions. And typically you set zone 1 to 89% of the first line, and then set zone 2 to overreach this bus. It's always overreach this bus, and anywhere from 25 to 50% of the shortest adjacent line that's off this bus. And zone 3, you set it to cover both this line and the longest line that's off of this bus, and overreaching the third bus. Now, I will make some comments about zone 3. There's a lot of discussion as to whether they should be used or not, because they have gotten into a lot of trouble associated with the recent history of blackouts and stuff, where they have contributed, zone 3 has contributed to misoperations. So there is discussion going on in regard to the application of Zone 3. And that's particularly true with the use of microprocessor relays, since in years past your backup was a Zone 2 relay. You had a Zone 1 and a Zone 2 relay. Well, anyway. All right. Zone 1. You do not want Zone 1 to reach beyond the remote bus. 10 to 20% margin. Okay, and this is to address inaccuracies that may be in the relay measurement, the current and potential transformers, calculated line impedances, etc. Zone 2 operates through timer T2, some delayed time, at some coordination interval that allows the remote Zone 1 to operate for faults in this region here, okay? And so if this does not operate, then Z2 will eventually operate, all right? And therefore, this Zone 2 is referred to as a remote backup to this Zone 1. Zone 3 operates through another timer, and again what you want to do is allow both Zone 1 and Zone 2 time to operate before this operates. Now you can probably see here you're getting into multiple contingencies here and why people are questioning Zone 3, because this would have to fail to operate and this terminal would have to fail to operate. And not only does this fail to operate, but this Zone 2 relay here fails to do the remote backup protection to here. So you're getting into some areas where, due to various conditions, some people are not necessarily using Zone 3s. Here's a case where Zone 3 is used in the reverse direction. All right, and this is pretty common for pilot applications, and where you want to detect reverse faults and with impedance relays and forward faults. Also, it can be used as a remote bus backup, such that this has an operating time that is slower than the Zone 1 to provide some type of backup to the bus protection here. Okay. Here's an operating profile using the conventional step distance, Zone 1, then a time delay, Zone 2, a time delay in Zone 3. What some people also do, particularly on sub-transmission lines that have a lot of tapped distribution load or tapped customer connections, rather than a conventional Zone 2 may have a time overcurrent characteristic, because on the tap load that may exist over here, you just may have time overcurrent relays. So you would want to coordinate that with the time overcurrent relays that are on this side of a tap load here. One of the issues with step distance is in-feed from the remote bus. In other words, I have a fault condition, and I also, over on Zone 2, in this region right here, I get not only the fault current that's flowing through the relay, but I get in feed from other sources to this point, which really affects the measurement in this region right here. And give you a little example here. Is that if I look at the fault current and the voltage drop, Ig times Zg, then here I've got Ig plus In times Zh, which is this voltage drop right here. I see the apparent impedance is Bg over Ig. That's all it can see down here. It can't see what Vh is. So there's this little quantity that's produced that is the increase in the apparent impedance. All right, and what that increase in that impedance makes that fault appear to be further away than it actually is. And therefore, you've got to be very careful in setting it such that you cover all the faults here. So it must be set to overreach bus H for in feed from bus H. This is zone 2, but not overreach bus K over here for no in feed. In this case, for no in feed at bus H. So you got to figure out exactly where to set it. Here's a case of outfeed, which is not really very common, and really what it boils down to is that you have a parallel path on the line to this fault. You have this branch, and then you have a branch that goes external to the line and back to the fault. And where this parallel combination right here reduces the ohms of this segment to the fault significantly to make the fault appear much closer than it actually is. So you just have to watch for conditions where this external branch can reduce the apparent ohms in this region to something lower than what it actually is. Switch on to fault conditions. What is the minimum voltage relay needed to sense in order to operate distance function? What is the minimum voltage relay needed to sense? Okay. I'll be discussing switch on to fault in a minute. Somebody asked me a question about switch on to fault, and we're not there yet. So we'll discuss that when we get there. All right, step distance, tap transformers. Again, tap transformers. You have a fault on this side. Again, you can go through the gyrations and see the increase in apparent impedance. And note that the apparent impedance will always be larger than the impedance to the fault. And then we talked previously about lines terminated into transformers. And here the issue here is that you would always like to use this current transformer and this voltage and do protection for this line. And always do separate transformer protection. The transformer generally has CTs associated with it, so you would want to use this CT and this CT to do transformer protection separately. Now, it may be that you might want to use the current or voltage from this side because it's available, typically voltage on the low side. But anytime that you do this, that you have to go through some means to either include the impedance of the transformer, because the distance is measured from where the voltage is done, and direction is measured from where the current is done. So there is a reference paper that Roger and I did a couple of years back that goes through this application in detail. It's probably a pretty good source. Source impedance ratio is the ratio of the source impedance to the line impedance. SIR to the relay, though, is the ratio of the source impedance to the relay impedance setting. The higher the source impedance, the more complex the protection, particularly with zone 1. Measurement errors are more pronounced. Current and voltage transformer error, CCVT transients. Current differential protection is really preferred, but may not be current differential protection is preferred in a lot of high source impedance applications. And then source impedance application of impedance relays or distance relays may not be recommended. The IEEE guide for protective relay applications defines what a short line is, medium line, and long line. And basically a short line is where you have SIR greater than 4. Again, this is a general term. I like to use it in reference to the impedance setting and the source impedance. That you should be using current-only systems, current differential or phase comparison, or some type of pilot system. Of course, on medium lines where the source impedance is less than 4 but greater than 0.5, you can do all of the above, but you can do normal step distance applications. And then where it's 0.5, where source impedance is less than 0.5, it's a long line application. But you can do all of the above, but and step distance systems. Non-pilot applications, Zone 1 extension. This is an application where your Zone 1 is initially set to reach beyond the remote bus rather than its conventional 80 to 90% value. It's set to reach. You have a fault over on this bus, all right? The relay here at A trips, the relay at C trips, and the relay at D trips. All right, they all high-speed reclosed, but Z1 is then retracted back to the 85% value. And when it recloses, the Z1 will be with this characteristic. If the fault is still there, then C and D will retrip and lock out. Okay, but this does not operate at this point. If the fault is gone, everything's restored. So it's a low-cost, I say low-cost, it's a method of trying to get simultaneous tripping. You end up with an extra reclose, but you get simultaneous tripping for applications without the use of communication-assisted schemes. Okay, then you have load loss trip, and the idea is along a line like this where you have a fault, and this is a non-pilot scheme, and where you have this fault, this breaker trips fast at B, and the relay at this end senses the loss of the balanced load. Hence, this application is good for all faults except three-phase faults. So it senses the balance load is gone, and therefore will bypass the timer for zone 2 and go ahead and trip. switch on to fault logic, there are two methods. There's basically, well, first you start with knowing the breaker position. It's either with a contact or having some type of deadline logic. And when the breaker at relay A closes, the SOTF works when I and not D operates, when you get a current and your voltage hasn't fully restored. Typically, people may set this voltage value here, okay, to 70% or 80% of the system phase to ground voltage. Set it up high because your voltage should certainly restore to a value greater than that. Then you can also use an overreaching zone that may be a impedance characteristic, looking in all directions, where you're looking at that element to operate, okay, if there is a fault on the line when you close. The question is, what is the minimum voltage relay needed to sense in order to operate a distance function? Distance functions can operate generally with a voltage almost all the way down to 0. I'm probably not understanding the question, and generally you're expecting to see that voltage restored pretty fast within a cycle, actually. You have stub bus protection. This is where the line is taken out of the service, and you have a breaker and a half or type of bus scheme, ring bus maybe, where this line is taken out of the service, and you have these two breakers here, and you may have a fault in this segment. So basically, what you do is you're measuring the sum of the current flowing into here, and putting a little timer associated with it to trip for a fault, a current that's measured there. Communication-assisted schemes. The goal of communication-assisted schemes is high-speed simultaneous tripping for all terminals. You have a normal reach, you have zone 1, and if the fault is outside, you would have to wait for zone 2 time. But in reality, what you would like is for both breakers to be operating simultaneously. Most of the schemes used are referred to as directional comparison schemes. It uses directional relays to determine fault direction relative to protected line at each terminal, and communicates that information to the remote terminal. I say directional relays, that also includes impedance relays. Not impedance relays, but mode distance relays or quadrilateral characteristics, or any of those characteristics that direction is part of. Communication channel requirements depend on the type of directional comparison logic applied, but usually needs only simple communications. I'll talk to you about 5 schemes: direct underreaching transfer trip, also known as intertrip; permissive underreach transfer trip; permissive overreaching transfer trip; directional comparison blocking; and directional comparison unblocking. The latter two are associated with power line carrier applications, and Generally, the permissive, overreaching, transfer trip, and the three schemes at the top here are associated with, in the past, has been some type of analog channel, microwave or something, or tone channel. And in today's environment, these are all done digitally with digital channels. Pilot relaying requires that each terminal communicate with all other terminals on the protected line. Your channels, again, I've already mentioned what they are. This is power line carrier, and power line carrier deals with the protected relay, a line tuner coupling that channel or high frequency channel up to the line, and then tapping it off at the line at this end. At this, you have line trap set at that frequency. You either have on-off keying or what is referred to as frequency shift keying. Directional comparison blocking is a method that is commonly used over this. On-off carrier is typically used, but you can use frequency shift. The idea of this primarily is that you're sensing a forward or reverse fault at each terminal. Therefore, if the fault is external, the 21S operates, sends a blocking signal to the remote end to block it. All right, and at this remote end, you generally have a coordination timer, okay, such to wait for this signal. If the fault is forward, then your 21 operates, nothing occurs, okay, and this unit right here has a 21, and it will be allowed to operate. Okay, again, this is referred to as a blocking, because if this sees the reverse fault, it will block at this point. Blocking systems are very dependable, do not require channel for tripping, can use distance or overcurrent relays, can use on-off or FSK power line carrier, inherently handles open breaker and weak in-feed conditions. Disadvantages: it's less secure. It may have a tendency to overtrip. If the channel is slow for some reason, if somebody leaves the channel switched off after maintenance. You also have a condition due to poor maintenance of the tuner equipment that produces carrier holes. Channel normally off and requires periodic checking, because the channel doesn't come on until you have an operation. So some people have systems they call check back systems and stuff like that that allows checking the channel once in a while. Now, you have directional comparison unblocking. Well, you use the term blocking, and now you have a term unblocking, where this end is normally blocked. This end would send an unblocked signal. Now, again, this is over power line carrier, but it requires FSK, frequency shift. So you're sending two signals, a channel trip signal and a channel guard signal. And what this allows for really is in this area of the logic here that because faults on the line may compromise the channel, okay, the communications through the fault, okay, that if you should happen to have a fault, okay, and your forward elements operate, your 21 phase and ground element should operate, then there is a 150 millisecond window in which it's allowed to trip if it does not receive a trip or a guard signal. So both ends should always be receiving a trip or guard signal. So when they lose the channel, no trip or guard, they've got 150 milliseconds to trip after a fault is sensed. The advantages: can use distance overcurrent relays. They're very secure. Continuous channel monitoring with 150 milliseconds trip window after loss of channel. Disadvantages: require special schemes to handle weak in-feed and open breaker situations. Well, that's not so much of a disadvantage, but they're good systems. Direct underreaching transfer trip. These systems are normally not applied to but can be to on-off carrier. But in this case, really what it is you set up zone 1, okay, an underreaching element that if it sees a fault condition, it sends a trip signal to tell B terminal to trip. That's basically what it does. Very simple. It's secure with good communications, but it doesn't protect the full line if one terminal is open. For example, if this end is open, you can't protect it if this region doesn't see it. Then you have permissive underreaching transfer trip. Again, you do the signal based on an underreaching element. So my zone 1 senses the fault. It sends permission to this end, but at this end I have a overreaching element. If it is operated, then it will allow me to trip, just in case that fault is down here and the zone 1 from this end can't see it. It's looking back with an overreaching element. There is a question I'm going to answer in just a minute. I'm going to go ahead and finish this group of slides. Permissive underreaching is more secure than direct underreaching transfer trip. It does not protect the full line if one terminal open, requires ground distance relays for accurate reach. Then you have permissive overreaching transfer trip. Is probably one of the most common systems outside of the blocking system. And basically what it does is if this 21 relay sees an overreaching fault, it will also send a permissive signal to this end. If this end also sees an overreaching fault in this direction, it must be an internal fault. It will go ahead, it will also send permission down here, and it will go ahead and trip. And the communications is either digital or tones. And it's very simple logic. Advantages: can use distance overcurrent, it's very secure. It's continuous channel monitoring. Disadvantages: will not trip for internal faults with loss of channel, and require special schemes to handle weak and in-feed and open breaker. Well, that's pretty simple logic, the last part. Then here's the weak in-feed logic in basic. That basically you have a very weak source down here that will not allow you to sense a fault. All right, and what you do is monitor the voltage at this point, and so you have a fault condition, and you have if you detect reverse current, well, obviously you see the fault in reverse. It's not on the line, but if you do not, if you see a low voltage condition and no forward current, then obviously it must be a weak in-feed condition. So you end up echoing a permission from this end back to this end to go ahead and trip the strong source. Okay. And here are some references that are just some good references to refer to. Now, someone had asked me a question in regard to the how does SOTF work when the VT is on the bus side? Well, that's the only time you ever, on the bus side. Well, you don't need it when it's on the bus side. That's the whole point. You use SOTF when the voltage transformers are on the line side. When it's on the bus side, before you close that breaker, you better have the bus voltage there. But anyway, I hope that addresses the question. And with this, I will transfer it back to Tracy. Hello. Ryan? There, okay.
Hi, Elmo. Thank you so much. There are a few questions, Elmo. I think Ryan is sending them to you through the chat feature. Do you want to try and answer them in the next few minutes that we've got some time?
Okay. The last question I have from Ryan is, are you done? Let's see. I addressed the one that says slide 63 related to software. How does SOTF work when the VT is on the bus side? You normally don't apply it when it's on the bus side. Because you don't need it. And then SOTF, where you want to apply it is where the voltage is at zero and when you're energizing a dead line. So you want to make sure there's no fault on that line, and you expect that voltage to come back within a cycle. And if it doesn't come back, then you trip it. All right, then is it a good idea to use a distance relay to protect a series compensated line? Well, it can be done. It can be done. I would always say that a series any line that requires communication assistance, I would go ahead and use phase segregated current differential. That is the best protection you can have for series compensated lines. Distance relays can be applied, but there are things that you have to do to make them work correctly, and it's quite complicated. Let's see. I'm not understanding. How can you discern or discriminate errors to do a compensation when the side of the line is weak source and you use this measurement of voltage and current. I don't understand that question, Ryan. Okay, it doesn't. I'm sorry. There's a question that I don't know how can you. I don't know if it means discriminate or discern errors. Let's see. All right, here's another question. When do you have a weak source in a side of a line and you use this measurement? The impedance calculated by the relays have errors. The error is lower when you have a heavy source. The side. Okay, I'm not sure of the question. I'm going to take a wild guess. Typically, if we're talking about a weak source, a weak feed logic, if you have a weak source, that means that you do not have a sufficient source in that when that weak source is looking forward to pick up an impedance relay or overcurrent relay in the forward direction. All right, and so you're sitting at that terminal in that condition. And if you receive a signal from the remote end, a permission to trip, and you can't sense a forward fault, the only thing you have left to sense is, do I have a low voltage? Okay, because I can certainly have a low voltage there with a very weak source. So because if I have a fault on the line, it's going to keep that voltage there. Okay, I mean it's going to be down. Now, if the source behind me that's weak changes and becomes strong, then you block the weak feed logic and just allow it to trip normally. So it depends on, you know, if occasionally you have a weak feed and other times you have a strong feed, then it doesn't matter, because if you sense a forward fault, you block the weak feed logic typically. I hope that addressed the question. Any more questions, Ryan? He said that's all he has. Okay.
Yep, I think we're good, Elmo. Thanks so much. I appreciate everybody's indulgence as we work through the technical difficulties. Elmo is in a different location than we are here, and so communication is a little bit challenging, and two screens is even more challenging. So we appreciate your patience. Thank you for attending today's webinar. When I close the screen, you will see a short survey of today's event. Please be gentle considering our technical challenges. We do appreciate your feedback and comments, and we very much appreciate your participation. Hope you had an informative session with us today, and we hope to see you next time. Thanks so much. Bye-bye.